Now let's consider the case of interaction of radiation with matter in the language of time-dependent perturbation theory. We know that whenever there occur interaction of radiation, in the sense that electromagnetic radiation with matter, generally there occur either absorption or emission of radiation from or to the incoming electromagnetic radiation by matter. Of course, there are some other phenomena like Compton scattering, photoelectric effect, etc. etc. We will be limiting our discussion to analyze the interaction of electromagnetic radiation, particularly in the visible range with matter. And of course, we will have to make a qualitative analysis of the mechanism by which this interaction takes place, with the help of the inferences that we draw by considering the interaction of electromagnetic radiation in the visible range with material medium. What will be the possible mechanism which will be occurring when there occur interaction of matter with electromagnetic radiation in the higher or lower wavelength regions comparing with visible range. We know that a plane electromagnetic wave can be represented in terms of the wave equation satisfied by the vector potential A as del square A minus 1 by C square dou square A by dou T square is equal to 0. Of course, this will be always satisfying the Lorentz gauge conditions V equal to 0 and del dot A is equal to 0, V equal to 0 as and del dot A equal to 0. These are referred to as the Lorentz gauge condition. I hope you will be able to recall this from your classes on electrodynamics in semester 1. These conditions are satisfied by electromagnetic radiation that is propagating at a very large distance away from the source of electromagnetic radiation. Though the source has a vector potential A as well as a scalar potential, say V or phi, since the electromagnetic radiation as a plane wave is propagating at an infinite distance from the source, we will be able to take these conditions phi equal to 0 and del dot A is equal to 0. The solution of this wave equation is A equal to, of course, this will be an exponential term with a coefficient I for the power. A of r comma t is equal to A0 of omega, the amplitude of the vector potential, e raised to plus or minus I into k dot r minus omega t. So of course there are two different solutions corresponding to this plus sign and minus sign. Then the most general solution can be taken as a linear combination of these two solutions. We take this as A0 of omega e raised to I into k dot r minus omega t plus e raised to minus I into k dot r minus omega t. And this indicates that we have a monochromatic electromagnetic radiation or wave having angular frequency omega and wave vector say k propagating. However, we seldom have this kind of a practical monochromatic single electromagnetic radiation. Instead, this always will have a spread of frequency around omega, so that the practical case of electromagnetic beam of radiation can be taken as A of r comma t is equal to integral A0 of omega e raised to I k dot r minus I omega t. I have opened this bracket as well as this bracket, plus e raised to minus I k dot r plus I omega t into d omega. So this will be the most suitable representation of electromagnetic radiation in the practical scenario, and you will be able to observe the fact that this is a time dependent parameter, and whenever there occur interaction of this kind of an electromagnetic radiation with a material medium, the material medium, as you know, will be always consisting of electrons, and these electrons will have a Hamiltonian which is equal to the sum of the kinetic energy and potential energy. The kinetic energy is represented by P square divided by 2m, or P square over 2m plus V. So this is the Hamiltonian possessed by the material medium. When there occur interaction of this kind of a vector potential with this material medium, of course there occur a correction in the Hamiltonian for the electron present in the material medium with which there occur an interaction. So definitely this can be viewed as a case of perturbation, and we will have to first of all identify the perturbed part of the Hamiltonian. For that, we will be interested in identifying what kind of energy change that the interaction of electromagnetic radiation with matter can attribute to the material medium. Of course, this is in terms of the scalar and vector potential carried by the electromagnetic radiation. We represent the vector potential using the symbol A and the scalar potential, say phi. Phi has nothing to do with this particular case because the system will be satisfying, the electromagnetic beam of radiation will be satisfying the Lorentz gauge, and phi is equal to 0. Anyway, since we will be beginning with a general representation, we will be retaining phi. The immediate consequence of this vector potential A, whenever it interacts with an electron or a system having a linear momentum P, is to impart a modification for the momentum, because in fact the vector potential A is a component of momentum. Once you are going to multiply this by E by C, where E and C are the constants having the usual meanings. So the immediate impact of this vector potential is to change the momentum of the system from P to P minus EA divided by C. And of course, the scalar potential will be imparting an additional energy, say E phi. So we have the material medium having Hamiltonian H equal to P square by 2m plus V. Actually, this needed to be represented as a H0, but I have written this in the sense that this is the modified Hamiltonian representing the system where there occur interaction of radiation with matter, or the system involving the interaction of radiation with matter. So we will be replacing P by means of P minus EA by C, so that this is the Hamiltonian of the interacting system, or this is the Hamiltonian while the system is interacting with the incoming beam of radiation, plus V plus E phi. But we have taken E phi equal to 0 or phi equal to 0 as this is necessitated by the Lorentz gauge. So we will be omitting E phi. I have retained this for 1 or 2 steps, but you can omit it right now itself. So this is P minus EA by C whole square by 2m. You will have to square this. These are operators, both P and A are operators. So P minus EA by C whole square has the meaning of operator P minus EA by C operating over itself. P minus EA by C operating over P minus EA by C. Of course, you can put the operator notation. So P into P, or P operating over P is not P into P. That is P square itself by 2m plus V also I have written, and I will be writing the remaining terms together. For this term involving the product of P and EA by C, that will be repeated corresponding to these two terms and these two terms. We will have minus common. So minus E by C whole divided by 2m is taken out, minus E by 2mc into, the first term will be P dot A. P square or P operating over P has the meaning of P dot P. P dot P is being written as a P square as usual. So this is actually P dot A, and this minus is taken out, minus E by 2mc. There will be A dot P. So actually this is plus, and I have made a mistake here. This is P dot A plus A dot P plus E phi. But what about P and A? These are common. P is actually momentum and A is in fact a component of momentum. The only change that the vector potential can impart to the system is to modify its moment. So A is in fact a component of momentum. And you have a theorem for the commuting operators. An operator will be commuting with all of its power, and again an operator will be always commuting with, or the different components of an operator will be always commuting. This is again shown by the Heisenberg's commutation relations. Commutator Pi Pj is equal to 0. Commutator Qi Qj is equal to 0. Whereas commutator Qi Pj is IH cross Kronecker Ij. So components of momentum are commuting among themselves. So P dot A and A dot P are commuting. So I can write this as a 2 times P dot A or 2 times A dot P. I'll be writing it as a 2 times P dot A. So this is actually minus E by 2mc, and this term is in fact a C. This minus sign is in fact a plus sign. Now I'll be writing this as a P dot A plus A dot P as a 2 times P dot A on the basis of this argument of commuting operators or commuting nature of the different components of one and the same operator. So I'll be writing 2 P dot A here. I have beaten around the bush for this particular step. You can write it say 2 times P dot A, so that 2 will be vanishing, and I will have this term modified as a E by mc into P dot A. This I will be omitting. This is now P dot A. I have already told you that I have omitted this term E phi. Now compare this Hamiltonian with the Hamiltonian of the system before the interaction, which is P square by 2m plus V, and this term is absolutely present here. So this is nothing other than H0, the Hamiltonian of the system before the interaction with the incoming beam of radiation. Then definitely this is the perturbed part of the Hamiltonian. Of course E phi is there, but Lorentz gauge has given me the flexibility to choose this term as say 0. So I precisely write it here in this step, say 0. So the perturbed part of the Hamiltonian is minus E by mc into P dot A. So perturbed part of Hamiltonian is minus E divided by mc into P dot A, where P is the momentum operator and it has a format that is known to me, which is minus IH cross grad. Minus IH cross grad. For P dot A and A dot P are commuting, so let me take it say minus E by mc into A dot P. That will give me a format for this perturbed part of Hamiltonian. So I'll be writing, since P dot A, P and A are commuting, P dot A is the same as A dot P. So I'll be writing it as a minus E by mc into A dot P. Now we replace P, the momentum operator, by means of its position representation or coordinate representation, not position representation, coordinate representation, that is minus IH cross grad. So minus and this minus vanishes. E by MC into, so that is minus E by MC into A dot P. We replace P by means of minus IH cross grad. So overall this make minus minus make it plus E by MC A dot IH cross grad. That is IEH cross by MC A dot grad. So the perturbed part of the Hamiltonian is IEH cross by MC to vanishes A dot grad. Thus, when there occur interaction of radiation with matter, there actually happens a perturbation for the material medium interacting with matter, or the electrons, atomic or molecular electrons present in the material medium that is undergoing this interaction with the incoming electromagnetic radiation. As a consequence of this, there occur a modification for the Hamiltonian of the system by an amount equal to IEH cross divided by MC into A dot grad, where A and grad are operators. Grad has to operate over the parameter that is to follow it. In this case, A is given by this equation, A equal to integral A0 of omega e raised to ik dot r minus I omega t plus e raised to minus ik dot r plus I omega t into d omega. So by substituting this expression for A, we will be able to modify this perturbed part of the Hamiltonian. And generally, we will be interested in analyzing the interaction of electromagnetic radiation in the visible range with matter. For the radiation in the visible range, there can be an approximation for this term e raised to plus or minus I k dot r. We will make that approximation here. E raised to I k dot r, of course, will be having a expansion for this exponential term, which is e raised to x is 1 plus x square over 2 factorial plus etc. So this will be 1 plus ikr plus ikr whole square over 2 factorial ikr whole square by 2 factorial is 2 itself plus etc. So this is an exponential series in terms of say kr or ikr. If you are taking the real part, this will be in terms of say kr. And k is the wave vector given by the expression k equals 2 pi divided by lambda. In the visible range, wavelength lambda, as you know, is in the range 4000 to nearly 8000 angstrom. Generally, we take the midband wavelength for this kind of approximation, which falls in green region and is of the order of, or blue-green region and is of the order of say 5000 angstrom. 5000 angstrom is 5000 into 10 raised to minus 10 meter, or in CGS this is 5000 into 10 raised to minus 8 centimeter. That is 5 into 10 power. You have 3 zeros cancelling with 3 and making it as say 5 into 10 power minus 5 in centimeter. 5 into 10 raised to minus 5. Then k will be equal to 2 pi. 2 pi has a value 6.28 divided by 5 into 10 raised to minus 5. So 5 into 10 raised to minus 5, that is to divide 2 pi. So 2 pi, as you know, is 6.28 by 5 into 10 raised to minus 5. 6.28 by 5 is approximately equal to 1. So 1 into 10 raised to minus 5 come to the numerator to make it say 10 raised to plus 5. Then what will be k dot r? K dot r will be approximately equal to, we have found this value of k of the order of 10 power 5 into r. R is approximately equal to the dimension of the atom. Dimension of the atom is of the order of 10 power minus 8 in centimeter. This is also known to you from the Rutherford scattering experiment. Atom has a dimension of the order of 10 power minus 10 meter, or in centimeter it is 10 power minus 8. So k dot r will have an approximate value of the order of 10 power minus 3. Now you look at this expansion, e raised to ikr. If it is plus or minus ikr, the first two terms will be 1 plus or minus ikr. Okay, actually this is k dot r, or say kr, if you take k and r along the same direction. So this is ikr, and kr has a value of the order of 10 power minus 3. So comparing with the first term, unity, the second term is 1000 times lesser, and the third term is 10 raised to minus 6 times lesser comparing with the first term. So even from the second terms onwards, you can neglect the presence of these values as long as wavelength of radiation of the order of 5000 angstrom or in the visible range is concerned. So in the visible range, we can take the first term e raised to plus or minus I k dot r in the expression for the vector potential to be equal to unity. That simplify the vector potential of visible light as A equal to integral A0 of omega e raised to minus I omega t plus e raised to plus I omega t into d omega. Keep in mind this is valid in the case of radiation in the visible range. If the wavelength in the X-ray or gamma ray region is concerned, which has a wavelength further lesser than that of light or radiation in the visible range, this approximation will not be valid, where we will have to modify the approximation by retaining some of the terms. So the Hamiltonian of the system, when the interaction occur with radiation in visible range is concerned, becomes h prime equal to I e h cross by mc integral, actually a dot grad. A is approximately now equal to integral a0 of omega e raised to minus I omega t plus e raised to plus I omega t d omega dot grad. Now this is a vector. A0 of omega is a vector. Grad is a vector operator, and we have to account for the dot product of these two vector quantities. As you know, the dot product has a physical or geometrical meaning or physical interpretation. See, A dot B is equal to modulus of A into projection of B along the direction of A. That is modulus of A into B cos theta. If the angle between A and B is theta, you have two vectors here, say A and B. See, this is a vector A and this is the vector B, and this is the angle theta between them. Then B will have two different components, one along this direction, that is B cos theta, and along this direction which is perpendicular to this direction, that is B sin theta. So the component of B along the direction of A is B cos theta. That is B cos theta. And A dot B is in fact A into B into or modulus A into modulus B into cosine of the angle between them. So we can look into this in the sense that B into cos theta is in fact the component of B along the direction of A. That argument is valid here also. We take it IEH cross by MC integral e raised to I omega t plus e raised to minus I omega t A0 of omega, that is the magnitude of A0 of omega, into projection of grad operator along the direction of A, that I have represented as component of grad along the direction of A into d omega. So we have evaluated the exact format of the perturbed part of Hamiltonian of a system or a material medium when the material medium undergo an interaction with electromagnetic radiation in the visible range. Of course, we will now write down the expression for probability amplitude, which we have already solved, Ckn of t. This account for the probability amplitude of transition from an initial state n to a final stationary state k possible for the interacting material medium with electromagnetic radiation. That's equal to 1 by IH cross integral h prime kn of r comma t prime e raised to I omega kn t prime, where omega kn is the frequency difference between the initial state n ket n and final state ket k dt prime, where h prime kn is equal to scalar product k h prime n. Here k, ket k and ket n are only space dependent components. The time dependent component e raised to I omega kn t we have already made it here. So h prime kn is scalar product k h prime n. Here h prime is to be replaced by means of this expression. So this is equal to, we replace h prime by means of this one. Here IEH cross by MC is constant, IEH cross by MC, scalar product k. What remains in h prime is integral e raised to I omega t plus e raised to minus I omega t A0 of omega into component of grad operator along the direction of the wave vector d omega ket n. Now you look at this, ket k is space only dependent, and this operator has a time dependent part as well as a space dependent part. The time dependent part has nothing to do with this space dependent state vectors ket k or ket n. So we take the time dependent part outside. What remains is IEH cross by MC scalar product k. The space dependent part of this operator is grad operator or component of grad operator along the direction of the vector potential, that is grad subscript a ket n integral e raised to I omega t plus e raised to minus I omega t A0 of omega d omega. Now the operator part in which we are interested happens to be, say, scalar product k grad a n. We will have to modify this part of the operator into a more familiar one. For that, consider this operator scalar product k or operator part scalar product k grad a ket n. For that, consider the commutator of position operator with the Hamiltonian of the unperturbed system H0. That's equal to commutator r p square by 2m plus v. That's equal to commutator r p square by 2m plus commutator r v. This is commutator a comma b plus c is commutator ab plus commutator ac. But commutator r v is equal to 0 provided V is a central potential or provided V has only dependence over R. So that this is also a theorem, or this is also a problem that you might have done in your quantum mechanics first paper. Commutator of a variable and a mathematical function of that variable will be 0, or a variable will be commuting with any of its mathematical function. V, the position dependent potential energy, is in fact a mathematical function of position vector r. So r will be commuting with this mathematical function. So I have omitted that term. What remains is commutator r p square by 2m. Commutator r p square by 2m has operators r and p square. So 1 by 2m is constant and can be taken out. So this becomes 1 by 2m commutator r p square. Now again you have another equation for commutator A. Commutator A b raised to n is n b raised to n minus 1 commutator AB. We'll be making use of this result here. Yeah, you take this as an assignment. Question: prove that commutator A b raised to n is n b raised to n minus 1 commutator AB. To do this, you just have to decompose b raised to n as b into b raised to n minus 1. Now, this is commutator A, comma b raised to n minus 1. Make use of the standard result commutator A, comma bc is equal to commutator AB into C plus B into commutator AC. Split this term till you will be getting, say, commutator AB. Corresponding to this, you will be getting one commutator AB plus commutator AB raised to n minus 1. Go on decomposing this in this manner till you retain this result, nb raised to n minus 1 commutator AB. Here, instead of n, we have 2. Then this is 1 by 2m is taken out. 1 by 2m, n is written here, n is 2, 2 p raised to n minus 1, that is 2 minus 1, 1 itself, commutator Rp. That is n, that is 2 vanishing with these 2, what remains is p raised to n minus 1, which is p by m into commutator Rp. This is the standard Heisenberg commutator, or this is position momentum commutator, commutator xpx equal to ih cross, also commutator Rp is equal to ih cross. So replace this as ih cross p divided by m. So commutator Rh0 is ih cross p divided by m, where p is the momentum and m is the mass. But commutator RH is RH0 minus H0R. That is then equal to IH cross P divided by M. That is IH cross P is minus IH cross grad by M, because I have to obtain an expression involving this grad A. Minus I square make it plus 1 H cross square grad divided by M. Now you substitute or operate this equation on this scalar product to make it scalar product K RH0 minus H0R ket n is identical with scalar product K IH cross square. Actually this is IH cross P by M. IH cross P by M operating over ket n. Now you decompose this as scalar product K RH0 ket n minus scalar product K H0R ket n, that's equal to scalar product K IH cross P divided by M ket n. Now H0 operating over ket n is En0 ket n, and H0 operating over adjoint ket K is of course ek0 complex conjugate, but this is the eigenvalue of a Hermitian operator which is real, so that is ek0 ket R operating over ket n. So from this term you have scalar product K R En0 ket n minus scalar product K ek0 R ket n. That means scalar product K ket R ket n is common, and since En0 and ek0 are scalars, En0 minus ek0 into scalar product K Rn is equal to scalar product K IH cross P by M. We have evaluated it as say H cross square grad divided by M. All these are say deleted. H cross square grad divided by M operating over ket n. For h cross square by m, as these are scalar constants, scalar product k grad n is equal to En0 minus Ek0 scalar product k r n. For scalar product k grad n is equal to h cross square by m is taken to the right side, m by h cross square En0 minus Ek0 scalar product k r ket n. That is En0 minus Ek0 by h cross is omega nk. So that if I take a minus sign outside, this can be omega kn. Energy of the final state Ek0 minus energy of the initial stationary state En0 divided by h cross is frequency difference corresponding to this stationary states omega kn. So this is minus m by h cross omega kn scalar product k r ket n. Or you multiply this equation on both sides by E and take E to this operator domain. Scalar product k E grad A is equal to minus, here I have to make a modification. If I am multiplying here it by E, I will have to supply this E term here. Now you look at this. Actually, E is not required here. Scalar product k grad n is equal to some constant, and this constant happens to be this quantity minus m by h cross omega kn. Scalar product k r ket n. So this operator grad in this scalar product is identical with this constant multiplying this operator scalar product k r n. That is expectation value of grad operator, not expectation value. The scalar product of this grad operator between two stationary states is identical with this constant minus m by h cross omega kn multiplying the operator r between the same stationary states. So we make use of this argument to replace scalar product k grad a n. So if this is true for this operator grad and the total position vector r, this will be true for any components of these operators grad and the position vector r. So that if I substitute, say, the component of grad operator along the direction of A, I will have to substitute here the projection of the position operator along the direction of A. See, I am interested in evaluating this term here. I have the projection of this grad operator along the direction of A. So I can substitute it here. The operation of this operator is identical with this constant multiplying this operator, say RA. Now you multiply this equation on both sides by E, then this becomes scalar product k E grad A ket n equal to minus m by h cross omega kn scalar product k E RA ket n. So now I can replace this operator scalar product k. That expression actually involved in E, the charge of the electron. E grad A n by means of this quantity. We will be doing it in the next slide. So H prime Kn becomes, it was I E H cross by MC scalar product K grad A ket n integral e power I omega t e power minus I omega t A0 of omega d omega. So I will be taking this E to this operator domain, so that I can replace this quantity scalar product k grad A ket n by means of this operator scalar product k E R A ket n. So this is I H cross by MC. E is taken inside and this is replaced by means of minus m by h cross omega kn scalar product k E R A ket n. This is the result that we have found identical with this quantity scalar product k grad A ket n. Integral e power I omega t e power minus I omega t A0 of omega d omega. Now we have minus sign taken say here, I written here, H cross will be going and M also will be going. What remains is minus I by C omega Kn, scalar product K E R A K T N, integral e raised to I omega t plus e raised to minus I omega t A0 of omega d omega. Now the operator part of this equation is simply say this one, scalar product K E R A K T N. Then it means that whenever there occur interaction of radiation in the visible range with a material medium, this radiation will be accounting for a transition of the electron from an initial state Kn to a final state K. And this transition is governed by this operator say ERA. What is the significance of this operator ERA? Where E has nothing to talk much, it is the charge of the electron. Or it is the charge of the entity that actually undergo a transition from one of its permitted initial state to another permitted final state. And RA is the position vector of, or RA is the component of the position vector of this electron that actually undergo a transition along the direction of the vector potential, which is the driving force for this transition. So the vector potential actually forces the electron to undergo a transition from its present position vector R to a new position vector say R prime, corresponding to respectively the initial state Ket N and the final state say Ket K. And the operator then has a meaning of the product of charge of the electron in the position vector of the electron with respect to the positive charge center of the atom, that is the nucleus. So this operator is nothing other than one of the charge into separation between the two charges, and this charge happens to be the electron comparing with the positive charge of the nucleus. So this is nothing other than an electric dipole moment. So we can argue that the incoming radiation in the visible range will be seeing the atom with which it will have to undergo an interaction as an electric dipole, with the dipole moment being equal to the product of the charge of the electron and the position vector of the electron with respect to the nucleus. So the incoming beam of radiation will not be capable of distinguishing the individual charges in the material medium with which it is undergoing an interaction, and instead it will be identifying the material medium with which it is going to interact as a dipole. This kind of an approximation is hence referred to as the electric dipole approximation. And keep in mind that this approximation, electric dipole approximation, is valid or is true or is a valid approximation only in the case of electromagnetic radiation in the visible range. If you are considering electromagnetic radiation having wavelength lesser than the visible range or wavelength of the visible range, then the incoming beam of radiation will be capable of identifying the individual charges in the atom. And corresponding to that, there can be further dipole moments like quadrupole moment or octupole moment, etc. As long as the radiation in the visible range is concerned, it will be identifying the material medium as an electric dipole, and hence this approximation is referred to as the electric dipole approximation. Now we will be evaluating the transition probability. It is of course the square of the amplitude of transition, that is Ck1 of t, which is equal to 1 by IH cross integral h prime kn e raised to I omega kn t prime dt prime. It's a mathematical procedure only. You will have to replace h prime kn by means of this expression. This is now 1 by IH cross integral minus I by C omega Kn scalar product K ERI Ktn, and this is often referred to as the transition dipole moment mu Kn. Transition dipole moment. E raised to, of course, there is one more integral. E raised to I omega t, e raised to minus I omega t, a0 of omega d omega, e raised to I omega kn t prime dt prime. You simplify this, you have I vanishing, minus omega kn is constant. So, minus omega kn by h cross c, scalar product k ERA Ktn, that is the transition dipole moment. Integral a0 of omega d omega, integral 0 to t e raised to I omega kn. Yeah, we will be multiplying or combining these time dependent terms. Here there is a sum of e raised to I omega t and e raised to minus I omega t. So this bracket is to be opened using e raised to I omega kn t prime dt prime. So this becomes e raised to I into omega t plus omega kn t prime. Yeah, t prime is taken out, plus e raised to minus I omega t e raised to I omega kn t prime. That is e raised to I plus I into omega kn minus omega t prime dt prime. All these t's are primary t's, and the limit of integration is from 0 to t. Now you can have two different options corresponding to the majority or dominant character of either this term or this term, and respectively this will be creating, not respectively, see, this will be accounting for an absorption of energy from the beam of radiation, and this will account for an emission of energy from the beam of radiation, as frequency is increasing here corresponding to the summation, whereas frequency is falling here corresponding to this subtraction. So consider the case of absorption. Ck1 of t is equal to minus omega kn by h cross c, scalar product k ERA Ktn, integral a0 of omega d omega, integral 0 to t e raised to I omega kn, actually kn is the minus omega t prime dt prime. Thus, probability amplitude for absorption will be exactly the same as the probability amplitude for emission. However, there is more scope for absorption since the population in the lower energy states as necessitated by the Boltzmann's distribution will be comparatively greater than that of the population in the higher energy states. So, there will be more intensity for absorption than for emission. However, mathematically or theoretically, the probability for the probability amplitude and as well as the probability for absorption and emission will be exactly alike, and this is referred to as the principle of detailed balancing, which we have already seen. Anyway, we will be evaluating this for any one of the cases. I have taken here the case of absorption. Minus omega kn by h cross c, scalar product k ERI Ktn, integral a0 of omega d omega. We will be evaluating this integral. This is also we have done so many times. E raised to I omega kn minus omega t prime by I into omega kn minus omega in the limit 0 to t. When the limit is t, you will be having this term, minus when the limit is 0, you will be having e raised to 0, making it as a 1. Now we simplify it. You have I omega kn minus omega. Omega kn minus omega is to be taken for this integration. So I take I outside. Minus omega kn by ICH cross scalar product k ERI Ktn, integral a0 of omega e raised to I into omega kn minus omega into t minus 1 by I into omega kn minus omega d omega. Now what we do is that we take e raised to I into omega kn minus omega by 2 outside. To make it in a more convenient manner, I have substituted theta equal to omega kn minus omega into t. So these terms are repeated, e raised to I theta by 2 into e raised to I theta by 2 minus e raised to minus I theta by 2 by omega kn minus omega. This I is not here, I is already taken out. So this is this probability amplitude. Then the probability for transition is square of this amplitude, that is, yeah, here I have to account for a simplification. This is of the form e raised to I theta minus e raised to minus I theta. E raised to I theta minus e raised to minus I theta is 2I sin theta. So that I will be vanishing with this I, and I have this term becoming as 2 taken out, since you have 2I sin theta here. 2 omega kn, I have written only omega here, divided by ch cross this transition dipole moment mu kn integral a0 of omega d omega e raised to I theta by 2 is there, that is e raised to I into theta is omega kn minus omega into t into again e raised to I theta by 2 minus e raised to minus I theta by 2, that is being written as say 2 sin theta by 2. 2I sin theta is actually there, I will be vanishing with this I. So this becomes 2 sin theta by 2. Instead of theta, we have omega kn minus omega into t. Now, to evaluate the probability of transition, we have to take the square of this one. That is, square of this one is 2 square 4 omega kn square divided by c square h cross square 4 omega kn square c square h cross square mu kn square transition dipole moment square integral a0 of omega square sin square omega kn minus omega into t by 2 by omega kn minus omega whole square d omega. This is a double integral, so d omega will be repeated. Now, in a practical case, there can be only one direction out of the possible 3 dimensions. So this is the overall probability, overall theoretical probability. However, practically there could be absorption or emission only along that particular direction in which the electromagnetic radiation is propagating, or the propagation direction of the electromagnetic radiation. So the practical transition probability must be 1/3 of this expected theoretical probability. So I'll have to multiply the in order to evaluate the practical transition probability, I have to account for this correction. I'll be taking only 1/3 of this evaluation. So this becomes 4 by 3. These terms are repeated. Only in this step I have written it as a mu kn square, but I might have written it earlier. This is as the dipole moment of transition. Integral a0 of omega square sin square divided by omega kn minus omega whole square d omega. Now you look at this. A0 of omega is in fact the amplitude about which will be peaking about a particular value of omega. We cannot take A0 as the amplitude corresponding to a particular value. Instead, this corresponds to a range of value around omega, that is omega plus d omega. It is in that manner we have already considered a practical case of electromagnetic radiation. It will not be always monochromatic. Even if you are taking it as monochromatic, it will have a minute infinitesimal spread over a frequency range, and this parameter will be peaking around omega equal to omega kn. See, when omega kn equal to omega, this denominator will be tending to 0 and this parameter will be tending to infinity. So overall this probability will be tending to a maximum, will be showing a peaking nature corresponding to omega equal to omega kn. So you can take a0 of omega as a constant term corresponding to omega equal to omega kn and is taken out. What remains is to evaluate the total probability, you will have to evaluate this integral from minus infinity to infinity. Sin square omega kn minus omega into t by 2 by omega kn minus omega whole square d omega. This integral we have already evaluated while we derived the Fermi golden rule. We substitute omega kn minus omega into t by 2 as x, then dx equal to omega kn is a constant, derivative of this one is 0, minus d omega into t by 2 is constant and is taken. Again omega kn minus omega whole square is equal to 2 is taken to the left side, t is also taken to the left side to make it say omega kn minus omega equal to 2x by t, and square of this one equal to 4x square by t square. We substitute these values to make this integral as say identical with integral from minus infinity to infinity sin square x by x square dx into t by 2, and this is a standard integral which is equal to pi. So the transition probability under electric dipole approximation becomes 2 will be cancelling with 4 to make it say 2t, t is taken out, omega square divided by 3 h cross square c square dipole moment square a0 square into pi. Or the rate of transition, that is the transition per unit time is, or the probability per unit time is 2 pi t vanishes. In order to evaluate this rate of transition, you will have to divide this by means of t. We find that it is constant in time. 2 pi omega square by 3 h cross square c square omega kn. Yeah, that I have already taken. Omega kn square is there. Mu kn square. So the rate of transition, once again, it's a constant. It is independent of time. It is proportional to the square of the dipole moment of transition and square of omega kn. That is the separation between the frequency separation or energy separation between the initial and final states that are connected by means of a transition. It means that by elongating the exposure time, we will not be able to account for high rate of transition. We will not be able to force or compel a transition from an initial state to a final state by a prolonged exposure. This is the same thing that we identify or we come to an end with as long as this electric dipole approximation is also concerned. Here also you can see that always this transition either in the form of emission or absorption will be in accordance with the energy time uncertainty. Delta E into delta T will be of the order of H cross. That means by increasing delta T, you could not increase or decrease delta E. There is an agreement between the change in energy corresponding to transition and time taken for transition. So between two farthly placed quantum states, you cannot account for a transition by a prolonged exposure. So here also we find that this idea is complementary with the energy time uncertainty. With that, we come to an end for the discussion of electric dipole approximation. Now we will have to talk about the selection rule as long as the interaction of electromagnetic radiation with electromagnetic radiation in the visible range with material medium is concerned. In spectroscopic analysis, we will see that, or you will be seeing this in your fourth semester spectroscopy paper, that not all transitions, or this is something already known to you people as well, not all transitions are permitted. Not all transitions are equally probable as well. Of course, the probability will be depending upon the population as governed by the statistical distribution. However, not all transitions are permitted. There are transitions between some selected energy states, and these transitions are governed by certain selection rules, and the selection rules are thus those rules which corresponds to a transition. If these rules are satisfied, then there will be a transition, and if these rules are not satisfied between a final and initial quantum states, of course there is no question of any transition between these two states. We will now derive these selection rules of transition. There will be transition, or the transition is governed by means of the transition dipole moment given by mu kn equal to scalar product k mu ket n, where mu equal to the dipole moment. I will be writing here the dipole moment as, say, minus Er, where E is the charge of the electron and R is the component of the position vector of electron along the direction of polarization, or along the direction of the vector potential. When mu kn is equal to 0, then the probability amplitude corresponding to that transition is 0. That means that kind of a transition, or such a transition between an initial state ket n and a final state ket k are not allowed, or these are forbidden transitions. So there will be transition if and only if mu kn is not equal to 0. Then, in order to derive the selection rules, we will have to identify those situations where mu kn will not be vanishing. Then, when will mu kn be vanishing? Mu kn will be vanishing when this integration, or when this evaluation is 0. This evaluation includes, this is equal to, as you know, this is equal to integral from minus infinity to infinity over the valid range psi k star E r psi n d tau, or where d tau is the volume element, minus is written here outside. Then when this is equal to 0, there is no question of any transition. When shall this will be 0? We will be analyzing the various situations in which this will be tending to 0. Look at this. R is a odd function. When R is replaced by minus R, this will be modifying as a minus f of R. So this is an odd function. The integral of an odd function, as you know, is 0. So the first possibility for this to be 0 is that overall this integrand is having an odd parity. But we know that all the stationary states has a definite parity, and this parity is governed by the azimuthal quantum number, say L, minus 1 raised to L. When L equal to 0, the parity is even, or when L is an even number, the parity is even. When L is an odd number, the parity is odd. So the possibility that this is odd can be identified like this. When both this adjoint ket vector and ket vector has the same parity. If this is odd and this is odd, overall this has odd parity. If this is even as well as this is even, overall this has odd parity because R is an odd function. So this integrand will be 0 when both the initial quantum state and the final quantum state has the same parity, either odd or even. So, in order that there is a transition between ket n, the initial state, and ket k, the final state, there should occur a change of parity. If this is odd, this must be even, or if this is even, this must be odd. So that overall, this integrand will have an even parity. Since the vector operator R already has an odd parity, if any one among these two eigengets connected by means of a transition has an odd parity, overall this integrand will have an even parity. The only possibility for this to happen is that corresponding to the transition from this ket n initial state to the final state ket k, there should occur a change of parity. When there occur a change of parity, L will be varying by 1 unit. So the first selection rule is that delta L equal to plus or minus 1. That means only those transitions corresponding to which there occur a change of parity in terms of a change in the azimuthal quantum number by 1 unit, either lowering or an increment, are permitted. So that now you consider the transition between 1s state and 2s state in hydrogen or in any other system. Transition of electron from 1s state to 2s state. Will this be permitted or not? I'll tell you that this is not permitted because S has an azimuthal quantum number L equal to 0. Whether it is 1s or 2s, azimuthal quantum number is 0. So there is no question of any change of parity by 1 unit when there occur a transition from 1s state to 2s state or vice versa. So that there is no question of a transition of electron from 1s state to 2s state. Whatever may be the drastic situation to which you make an exposure to the system. Now another occasion in which this will be tending to 0 can be evaluated in terms of this representation. Ket psi k can be written as say ket n prime l prime m prime and ket n by means of ket n l m. So this scalar product is scalar product n prime l prime m prime minus er ket n l m. Now this will have a phi dependent part in the adjoint ket space, which is e raised to I m prime phi, and in the ket space this will be e raised to I m phi, and that part will be independent of this position dependent operator. So you can take this one outside, and this is integral 0 to 2 pi. Only the azimuthal angle part is taken into, zenith angle part is taken into consideration. Integral 0 to 2 pi e raised to I m phi into e raised to minus I m prime phi. Actually this is e raised to I m phi. From the adjoint ket space you will have to take the complex conjugate, then this becomes e raised to minus I m prime phi. Yeah, that is written here, e raised to minus I m prime phi. This is equal to Kronecker m prime m, since these two components are orthonormal. And this will have a non-zero value when m prime equal to m. That means when change in m between the initial and final state, or corresponding to the transition from initial state ket m to final state ket m prime, is 0. So there will be transition if and only if delta m equal to 0. And this derivation is valid when the polarization is along the z direction. Then you can easily take this e raised to I m phi as, say, in this manner. However, there can be one more possibility for the polarization. Polarization can be in the xy plane. If it is in the xy plane, then this term are needed to be decomposed in terms of, say, x and y components. For that you consider x as equal to 1 by 2 into x plus iy plus x minus iy. Iy vanishes, this is 2x by 2, which is equal to x, and y can be written as 1 by 2y into x plus iy minus of x minus iy, that's equal to y. You can take, say, this x vanishes, iy minus iy, make it, say, plus 2iy by 2i, which is y. Then x plus or minus iy is, as you know, in SPC, x equal to r sin theta cos phi and y equal to r sin theta sin phi. Then see here, this will have this component phi, and this component needed to be taken into consideration while you take the integral of this zenith part of the wave function. This is valid if and only if the polarization is in the xy plane. Then that will be giving a component along the zenith angle direction. So this is r sin theta cos phi plus or minus I r sin theta sin phi. So r sin theta is taken out. What remains is cos phi plus or minus I sin phi, which is e raised to plus or minus I phi. So when the polarization is in the xy plane, there is one more component for the phi part. Besides this term e raised to I m phi into e raised to minus I m prime phi. Then the integral becomes scalar product n prime l prime m prime x plus or minus iy get nlm equal to, this is retained, x plus or minus iy is replaced by means of r sin theta e raised to plus or minus I phi. Now you take the phi dependent terms and the product of all the remaining is taken as a mathematical function of r and theta only. This is now integral. Of course, integral is there. E raised to I into m minus m prime coming from this one, plus or minus 1 coming from this one, phi d phi. Now, under what kind of a situation this will not be equal to 0? This happens when, or this can be written as a Kronecker m comma m prime plus or minus 1. This Kronecker will be equal to 1 when m and m prime plus or minus 1 are equal. See, Kronecker will have a non-zero value when these two indices are equal. Here the indices are m and m prime plus or minus 1. So when these are equal, you can write m prime, m minus m prime, where m is the magnetic quantum number of the initial quantum state and m prime is the magnetic quantum number of the final quantum state, that is the quantum state after this transition, which is equal to plus or minus 1. So in such a situation as well, the transition is permitted. So only those transitions that are satisfying these conditions are permitted, and hence these are the selection rule for transition as long as the interaction of electromagnetic radiation with matter is concerned. So these transition selection rules can be stated as only those transitions that account for a change of azimuthal quantum number by 1 unit are allowed. Only those transitions that account for a change of magnetic quantum number by 0, there is no change, or by 1 unit are allowed. Now you consider the transition between 1s state and 2p state. Whether this transition is allowed or not, transition from 1s, transition of an electron from 1s state to 2p state, 2px or 2py or 2pz, whatever may it be, is permitted or not. Let me take it, say 2pz for the time being. So I'll have to check into the first selection rule. S state has an L value that is equal to 0. P has an L value that is equal to plus 1. So as per the first selection rule, change in L value corresponding to this transition is 1 minus 0, that's equal to 1. So this selection rule is valid. So according to this selection rule, this transition is permitted. Now we'll have to look into this case. M value corresponding, when L equal to 0, M can have only one value, that is 0. See, M has value minus L through 0 to plus L. And corresponding to this one, when L equal to 1, M will be minus 1, 0 and plus 1. Suppose, see, this corresponds to pz, this corresponds to px, and plus 1 value corresponds to 2py. Suppose the transition is from S to this. When corresponding to, say, L equal to 1, you can have three different choices of m. M can have -1, 0 and +1 as the three possible values. Suppose the transition is from 1s to 2p, 1s to 2px. The change in m value is 1, that is -1. When the transition is from 2px to 2pz, change in m value is 0. When the transition is from 1s to 2py, then also the change in m value is +1. So, corresponding to the transition from 1s to 2p, whether it is 2px or 2py or 2pz, all these are permitted since all these transitions satisfy both of these selection rules. So, transition from 1s to 2p is possible or is permitted, whereas transition from 1s to 2s is not permitted. So, using this selection rule, we will be able to distinguish the permitted transitions, or we will be able to identify which transitions are not permitted. With that, we come to an end for this module, and now we'll see the exam point of view as long as this module is concerned. Generally, you will be getting one question in each of your sections in the question paper. These are the most frequent short answer questions. You'll be asked to define Fermi golden rule. You just have to make the statement of Fermi golden rule and write down the equation. One of the most frequent short answer question is electric dipole approximation. What is electric dipole approximation? You will have to start with this equation. Here is to ik dot r is equal to 1 plus ikr plus ikr whole square over 2 factorial plus etc. When light in the visible range is concerned, this is approximately equal to 1. In such a situation, the incoming radiation will be identifying the material medium with which it is interacting as tiny electrical dipoles, and this approximation procedure is hence referred to as electric dipole approximation. Another possible question, and this is also asked many times, principle of detailed balancing. In harmonic perturbation or in interaction of radiation with matter, there is possibility for absorption as well as emission. Theoretically, the transmission probability for emission and absorption can be proved to be exactly identical, though practically absorption will have more probability comparing with emission, and this is referred to as the principle of detailed balancing. Now you will be asked to distinguish between stimulated emission and induced absorption as a case of harmonic perturbation. Another possible short answer is you may be asked to derive the selection rule of transition. The most frequent essay is the derivation of Fermi golden rule. You will have to begin from time-dependent perturbation theory, evaluation of the general formula for the transition probability amplitude of transition. By taking the square of this one, you will be able to find the probability. Then you will have to discuss the case of either constant perturbation or harmonic perturbation. Using that case, you will have to make the statistical analysis that will permit you to evaluate the Fermi golden rule. We state that the transition probability or rate of transition is not transition probability. It is transition probability per unit time, or rate of transition is constant in time, and it is proportional to the square of the matrix element of transition, which is referred to as the Fermi golden rule. So the rule indicates that you cannot account for a transition between two farthly placed quantum states by means of a prolonged exposure. Now, problem section. You may be asked to identify the permitted transitions among a set of transitions. Which out of the following transitions are permitted? 1s to 2s, 1s to 2p, 3s to 5d, etc., etc. You might have given 5 or 6 choices, and you will have to identify the permitted transition. Another possible question is the probability. This question is being asked as a problem question. Last but previous year, you were asked to, the candidate was asked to evaluate the probability of transition in electric dipole approximation. So with that, we come to an end for the discussion of this module. Have a nice time for your study, and I pass the ball to you people. Thank you.